listening to a topic which is very important to astronomy and potentially to all of us because it concerns the subject of planets outside of our solar system, planets that are around other stars. And you may know that for about 50% of us in this audience, the first extrasolar planet was discovered within our lifetime. I remember learning as a graduate student that we don't think that there are any planets around other stars except for the sun. And that turned out to be grossly wrong, as J.D. will tell us tonight. J.D. I've known for, seems like about 300 years, but it's not that long. J.D. and I go back to Michigan State days when we were there. J.D., as you may not know, studied nuclear physics for a long time. And then after deciding that that's a dull and uninteresting subject whose time has come and gone, joined us here in Hawaii and got his PhD, we think, in 2004. J.D. joined us here in Maui about 5 years ago. 5 years ago, and he is the only professional astronomer at the IFA who spends a whole lot of his time interfacing with our general mission, which is education to people that aren't professional astronomers. We all have that as part of our mission at the university, but JD takes it seriously. And so it really is a great pleasure to listen to him talk tonight. The other hat that he wears is the astronomer at the IFA who is most connected to the world's largest educational telescope, which is the Las Cumbres Observatory Fox telescope, which is right here on Maui, which he's often up on the mountain working on or fixing. So, JD, I'll give you this, and you can tell us all about exoplanets.
Oh, hasn't it been about 310 years, Jeff? Isn't that? Well, I'm going to close this door, see if we can take a little bit of light off of the screen. That's better, isn't it? Okay, so I am Dr. J.D. Armstrong. I work with the University of Hawaii Institute for Astronomy and also with Las Cumbres Observatory Global Telescope. They're the company that owns and operates the Fox telescope up at the summit of Haleakala. You'll hear a little bit about that. And as Jeff said, I do work with a number of students. And we've got two in the audience. If you guys want to, do you mind standing up and just waving at everyone? It's okay. That's close enough to standing up. They're shy. And then we've got one in the back that I'm trying to, yeah, Brian, that's, there's another student that hopefully will get in here. And I'm going to be, of course, talking about exoplanets. So, first of all, we need to establish some ground rules of what are exoplanets. And, well, exoplanets are planets that do not orbit the sun. Now, you probably want to drag me into the conversation of, is Pluto a planet, or is it a dwarf planet, or what is it? I'd say it's a comet, but let's save that debate for elsewhere. Okay? We're not going to be able to detect something as small as Pluto, so I think that anything we see will be large enough that we'll agree that it's either a planet or brown dwarf or star. So we don't have to worry about the Plutos of the universe. Now, scientists have discovered over 500 of these. I think it was 562 when I checked yesterday on Wikipedia. But we want to talk a little bit about how scientists know about these planets. You know, knowing that they're out there is one thing, but knowing why it is that we know that why we say these planets are out there, that's real science, and that's the way a scientist thinks. So here's another question: why should we care about extrasolar planets? We're not going to go to them in our lifetime. I think that's pretty safe to assume. But they do tell us about our own solar system. You know, they tell us, is our solar system unique or not? And as Jeff was saying, we used to think that most other stars didn't have planets. It was a very rare thing. And now we're beginning to say, well, probably most stars do have planets. So a very different thing. Is our planetary system just a coincidence? Do they change? The Earth's orbit has been in a position that has been good for life for a very long time. Do planetary systems tend to change in shorter time scales? Is this something that we should worry about for the future of humanity? Okay. Life may be found on exoplanets. I mean, we've all seen Star Trek. Where do the Romulans live? On a planet. You know, all these other societies. I think that it's pretty easy to convince most people that if you're looking for life, you should start on something that looks like a planet. And also just for pure science. So what we're going to do tonight is we're going to explore strange new worlds, seek out new life and new civilizations, boldly go where, well, we'll see some new planets that other people haven't seen, but not the first planets. All right, so let's start off. I'm going to be talking about the Phelps Telescope North mostly throughout this talk. This is the telescope I work with, and so of course I'm going to talk about, you know, this is an old friend. So this is a real image of a star field from the Phelps Telescope North, and this is actually one of the exoplanetary systems that students have studied. This is the star that has an exoplanet around it, and I want you to wipe your minds and say, well, why do we believe that? Just do we really trust JD? What does he have to show us that can convince us that there is a planet around there? That's the attitude I want you to listen to this talk. I have to convince you that there is an exoplanet around there. You can accept that these images are real, they're what I say they are, but you know, look at this and see if you're convinced whether or not there's an exoplanet there. All right? So if we zoom in, here's what starts to worry me. This is a picture of one of the stars. And I can zoom in a little bit more. You can start to see the pixels in the image. One more time. And so now you can really see, and the light is spread out over a large number of pixels. That's actually the telescope that is doing that. It is not the size of the star. Now in my abstract, when I announced this, I said that all the stars that we see are a point of light. And that's not entirely true. There are 4 stars that have been resolved. In other words, that we see images and we can get spatial detail out of. Does anyone know one of them? Betelgeuse. Okay. The sun. Okay. I can't remember the other 2, but I was just looking at it. It was on. No, it wasn't Antares. It might come to me, probably won't. But there are at least 4 that were listed in Wikipedia when I looked today, and there are probably a couple more. It has been done. They're very big stars. But for more typical systems, like the Phelps telescope, this is a 2-meter telescope that is within the atmosphere. This is more like what we're going to see. And for a typical star, it is much, much smaller than a pixel. I did a calculation. I can't remember what the star was, which star it was, but it was a relatively close star, and it was about 1/100,000th of a pixel across. That's the diameter of say, the sun at a reasonable distance. That's the type of thing we're talking about. All right, so let's look at a model here. So here's our pixel. Sorry, keep reminding Steph, please remind me not to use the laser pointer, because I know our friends in...
it's actually okay.
It's actually okay?
I'll use the,
okay.
Camera.
All right. If they can see it in Second Life, I'm happy with it. So here's our model of a pixel. This square is 1 pixel, and here's our star in the middle, and this is our planet's orbit. Okay? And we'll pretend we're looking for Earth around the sun. So it's 1 astronomical unit from the star. Okay, there's something I don't like about this. Let me adjust that. Star is actually much smaller, so let's adjust everything. That's a little better. This is the kind of thing we're talking about for a typical planetary system. Not all of them are like this. Okay, so if I want to convince you that there's a planet around that star, or you want to convince yourself, or we want to learn something about these things, well, this is for a close star. Well, that's not a good situation. All right. So, how can I convince you that this is indeed reality? Okay. So, the question is, from a single point of light, how do the scientists find these exoplanets? Most of these exoplanets are found by looking at a single point of light. First, we want to start with a few assumptions. Physics works everywhere else the same as it does here. So when we're watching Star Trek and they go to another planet and they hold something up and they drop it, it falls. Gravity is the same there as it is here. Chemistry is the same there as it is here. Science works pretty much the same way throughout the universe is one of our first assumptions. And in fact, we don't even have to go very far in the universe before we aren't even going to bother looking for exoplanets. So just even in our neighborhood is all we need to do for this assumption. There is evidence that this is true. We see things that are consistent with our descriptions of nature, our physical models, our understanding of science. And we also want to assume that stars are objects similar to our own sun. They're these balls of gas, hot gas. And we see evidence that that's true too. It's not just a fairy tale that we tell in classrooms and schools. It's the truth. Okay? And we have evidence to support that. We've taken observations and we put together these models. And that's the idea of science, is to take observations, put it together in a coherent story that explains something. And saying that stars are objects similar to our sun is an example of that. I'm not going to go into that any more than that. But so here are our assumptions. And here are some methods that exoplanets are actually detected. So direct observation. We look at an image, we see a star, we see an exoplanet. Okay? And I've already gone into that is very difficult to do. Proper motion. So as a planet orbits its star, it pulls the star around just a little bit, and we see it wiggle in the sky. So far, none have been detected like that. Doppler shifts. Look for the reflex of the star. That's kind of like, instead of moving like this, it's moving towards and away from us. I'll get into that one a little bit more. Transits. This is what I'll spend most of my time talking about, is transits, because this is what we work on with Falks. This is what I do. Microlensing. This is another project. It's general relativity, that the planet actually focuses the light a little bit more, so a background star becomes a little bit brighter. All right. So direct observation. Here's our planetary system. And so we want to see the planet orbiting that star. We want to identify, we take a picture, we identify which feature on the image is the star and which is the exoplanet. You've got to remember, these stars are 1 billion times brighter than the exoplanet nearby. It's very difficult to detect these. Tends to be tough because stars are very far away, and so they look very small. There's a bias towards finding very large planets very far away from their star. If it's too close, we can't resolve them at all. All right, and so here's our, so we zoom in on this, and you can see the orbit over here. There are 3 examples that I know of. There may be some more now where this has been done. This was taken with the Keck Observatory. This central noise in the middle is where the star was, and they use interferometry. They blank out the central star, and then you have these residual dots here, and those are the exoplanets. Those are planets that orbit that star, and they take an image later, and they see these dots moving in a way that is consistent with planets orbiting the sun. Okay, and here's another one, AB pictoris. So you've got an occulting disk here. You put a little disk in an image plane and then re-image it onto the camera, and then here's your little planet. This was really exciting. This is only about a couple of years old, and so I remember when they started announcing, "Hey, we took a picture of an exoplanet." This is from I think this is from Hubble. This is Fomalhaut, and so in 2004, here's this little dot here. 2006, here's this little dot here. That's their exoplanet. People in the back row are sitting here looking at me going, yeah, can't see it. So you can come up afterwards and take a closer look at this, or just Google it. It's on Wikipedia, all of these. Proper motion. This is when you have a planet orbiting a star. It pulls the star a little bit, it pulls the star around, and it seems to wobble in the sky. The reason that they mention this with exoplanets, even though no exoplanets have been detected using this method, the reason that I mention it is it's a very common way of determining if there's a binary star system. And so you actually, this came out of looking for binary stars. Doppler shift. This is about where 75% of detections come from. I was actually surprised. I would have thought it was transiting. But the idea is, if we look at the sun, there are these spectral lines. You see these dark lines in the spectrum. If we spread out light into its colors, the elements that make up the star leave a thumbprint on that light. And those lines are very precisely, have very specific wavelengths. So what we do is we look for a shift in those wavelengths. So if we're up here looking down at the star, then its velocity towards and away from us will cause a change in the color of those lights. So when it's coming towards us, it's blue shifted. It's the light, it's like the wavelength of light is squished a little bit. So it comes a little bluer. And then when it's moving away from us, it's red shifted. It's like the wavelength of light has been stretched out a little bit. You guys have heard of the Doppler effect when you've been sitting by a road, hear a motorcycle or a car pass, as right? Does that sound familiar to everyone? It's higher when it's approaching you because the sound waves are squished to a higher frequency. And it's longer when it moves away because sound waves are being stretched to a lower frequency. Yeah?
Now, couldn't they be confused with the wobbling of the star if there was a double star?
A double star?
Yeah, two stars that orbit each other.
Right. So the question is, couldn't they be confused if it was actually a double star? Actually, this method will put a limit on how big this other object is. So a star is much heavier than a planet, and so if they see something big enough to be a star, then they say, okay, not an exoplanet. All right? It's great. So the advantage of the Doppler shift is, like I said, you can put a limit on how massive the planet is because you know roughly the mass of the star, and you see how much it gets pulled around by the planet. But it's only a limit because the signal is the velocity of the star projected on the line of sight. It's only how fast it's moving towards and away from us. This direction doesn't give, up and down doesn't give us any Doppler shift. And so if this is the orbit, then it's only this component of the orbit that we actually see. It's only a portion of it. Okay, gravitational lensing. And this is a project that Las Cumbres Observatory is working on right now. Dr. Edward Gomez actually sent me an email saying, hey, if you've got any students out there that want to work on this, please let me know. We'd be very interested in having some more partners in Hawaii. The idea is that gravity can bend light. And so it focuses it. It acts as a very weak lens and focuses a little bit more light into the pupil of the telescope. And so as this exoplanet passes nearly in front of the star looks like it gets a little bit brighter. And here's sort of a cartoon of how that happens. There's actually a source star behind. The planet is orbiting another star, and then we're over here observing it. And I'm not going to answer any questions about this because I haven't worked out all the details in my mind yet. But I know it works because here's a nice curve that was constructed by Dr. Gomez. I believe that's where I got this. Using data from the Falks Telescope North, and students that he's worked with have also been doing this. Transits. This is the one. This is the money one for me. So let's imagine that there's a lot of stars out there with planets. Just by chance, some of them are going to line up, those orbits will line up so that the planets will pass between us and the star. Right? When that happens, the planet blocks some of the light from the star. Okay? We know the geometry, and we can measure precise timing of one spot in the orbit. So we can measure the period of the orbit, the planet's year, very precisely. This is very useful. In addition, when we have transiting planets, we can get supplementary information from the Doppler shift. We can, instead of putting a limit on mass, we know the mass because we know the geometry. Okay. So why am I so geeked about transits? I mean, 75% were discovered with spectroscopy. Why am I geeked about transits? Well, first of all, this is work using the Falks Telescope North here on Maui. That's the telescope I work with. I get geeked about it. It's fairly easy to understand. I mean, this gravitational lensing thing, that takes a bit of thinking. This is easier to understand, and so you can go on and do some more science with it. Okay? I'm involved in this work. Of course, that's a reason anyone would want to be studying transits. JD does it, right? Okay? And students are involved in this work, and I'll introduce you to some of the students later. In addition, we had, after I got some initial observations of transiting exoplanets, I shared them with the observations with Mr. Graham DeVay, who's a teacher over at Baldwin High School. He put together a program for his class, a lecture surrounding these observations that was so good. His principal said, hey, you know, it'd be a great idea. Why don't you give that lecture to every student taking science here at Baldwin High School? And so every year, we have Mr. DeVay, in fact, every semester, Mr. DeVay gives the talk on exoplanets. And this is Travis Lay. Travis went to the Intel International Science and Engineering Fair. This year was his third year attending. But the first year he went there, 14 years old, the National Association of Physics Teachers gave him third prize for his project on exoplanets. He's 14. I believe she was a junior and she was a senior in high school. That's pretty impressive, isn't it? And he was doing exoplanet work, so I was kind of geeked about that. And then, of course, the next year, we have a summer camp. The next year, we had Travis teaching the next generation of students. Okay? This is a really good idea. You know, have the students learn something and then teach it, because when you teach something, you really learn it. All right. So, but comes back to this. We've got a single point of light. Can we really tell that there is an exoplanet around there? This kept me up at night more than once. So let's think about this for a minute. Okay? Can we really tell anything from that single point of light? Well, let's start off by looking around and seeing what we do every day in our lives. What can we really prove? Okay? Well, I think, therefore I am. Okay, so I know I exist. I don't know about the rest of you, but I know I exist. I see you guys out here, so I have a theory that you exist. And my theory is that you're beings similar to me, that you think, and therefore you are. And I see you. I can test this theory. Let's say I say hello to you. Hello? Oh, very good. So I can now refine the theory. You guys can speak. You can do something similar to what I do. Okay? I can test this theory again. Do you see her? Do you see her? Yeah? Okay. Do you see this gentleman behind you? Okay. Okay, so the reason I chose these two is I know them. They're real. They're real to me. They already exist. So this is something that actually Dr. Nash used to do. Dr. Nash was a Nobel laureate that suffered from schizophrenia, and when he would meet a new person occasionally, he would ask somebody that he knew, do you see that person? Can you confirm that that person exists? So it's a self-consistent theory of, yes, all of you exist. Really, all I know is I am getting input from my eyes and from my ears, maybe from touch or whatever. I have sensory input, and I interpret that sensory input as you are people. Okay? But it's a theory that's self-consistent. All right? Now, most of a scientist's time, however, is spent trying to disprove theories. This is something that that was mentioned to me a few years ago, and I thought about it, and it's like, yeah, that's true. When you disprove a theory, that's when you get to say something new. All right. So let's look at our work. Let's look at our theory. Okay? We observe planets orbiting our own star, orbiting our sun. Okay? First of all, and I've been watching this, I see the stars moving through the sky in a way that's consistent with us orbiting the sun. I've been watching Saturn, and I've been seeing that move. It was very close to another star recently, and it's moved out so that it's now a couple degrees from that star. So I'm actually observing these planets and seeing, yes, they're moving in a way that's consistent, and they're orbiting our star. Okay? But even if we want to go so far as to take that on faith, then we can jump to the, we don't believe that this is a unique situation. Maybe it's rare, maybe it's not rare, but we don't believe it's unique. Okay? So our theory is that there are planets, and planets are large bodies that are not big enough to be called brown dwarfs or stars, orbiting other stars. We believe that that is the case, and we theorize that some of these planets will pass in front of their star. Let's think about what that would look like. Okay? So this is an image of the sun. I got this from the SOHO satellite. And there you see this dot moving in front of it. Okay, that's just an artificial spot that I put in front of there and animated. I move it along. And so we'll call that planet Puka. All right? And so as planet Puka transits its star, I can add up how bright this image would appear. And this is what I end up with. So before it transits, before the planet Puka passes between us and its star, the star is pretty constant. Then, as it starts to clip the star the star would appear to get a little fainter. A little fainter here. And then it reaches a minimum right at the center. And then as it comes out, it returns to its original brightness. Aren't you glad that I didn't make you guys line those up like I do with school kids? Okay. I give more quizzes to school kids. All right. So here is this exoplanet that I showed you in the star field earlier. It's called WASP-2b. It was discovered by the WASP project. It was the second one that they found, first one orbiting that particular star. Okay, so WASP-2a would be the star that the planet WASP-2b is found around. So we're going to take a series of images. We're going to take pictures of it, kind of like a movie. We're going to measure how bright the star is by adding up all the pixels around the star. Okay, here's the star. We're going to add up the brightness in everything everywhere in here, and we're going to plot that against time. And I already know that there is a star orbit or a planet orbiting this star, and I know that we're taking pictures when this planet is passing in front of the star. Okay, so we should see something very similar to planet Puka. All right, there you go. How many of you are convinced that this is an exoplanet? Raise your hands. Anyone in Second Life? Nobody. Ah, that's not surprising. This looks pretty junky, doesn't it? Okay, well, what could have gone wrong? You know, when I go outside during the daytime, I see that the sky is blue, and that means there must be light coming from different areas of the sky. And in fact, we know that there's light coming from the sky during the night. So what we're going to do is we're going to look out here, and we're going to kind of take a sample of that. And we're going to see if subtracting what we think the sky should be fixes our problem. Okay? There, is that better? I'm not convincing anyone? All right. Have any of you seen stars twinkle? Any of you sung a song about it? Okay, good. A couple of you were falling asleep. I wanted to catch you. Well, stars twinkle, and that's not just our eyes. Here's my theory. It's not just our eyes. Maybe it's the atmosphere. Okay, that's what scientists say. And so two stars that are fairly close together should twinkle together. So if I have two stars, don't know what happened there. Two stars here and here. If this one gets 10% brighter, then this one will also get 10% brighter. All right? Okay? So maybe they twinkle the same way, and we compare the two stars. So we take our target star here. This is the one that I said had the exoplanet. And then we have this other star up here, and we divide how bright our target is by how bright our comparison star is. And we also subtract off the sky and all those other things. Okay? This is called the target star, and this is the reference star that we compare it to the reference star. All right? There we go. Is that any better?
Yeah.
Is that a little more convincing? Anyone convinced?
People are waving in the virtual world too.
People in the virtual world agree. Good. So, and real world, some of you believe that that's a real planet?
What's the time scale on the bottom?
What's the time scale on the bottom? Time is in hours. Yes. The period of this planet, it's very close into its star. The period is 2.15, I think it is, 2.15 days, something like that. If somebody in the virtual world wants to correct me, I'll accept that correction. And since I know you're near a computer, it's WASP-2b. So basically, we can see it, the star dipping down the way we would expect. And let's look at them side by side. Is that fairly convincing?
Yep.
Okay? So we have observations. They match our model, our description. That's a pretty good thing. Another thing that we should expect, though, is shouldn't it repeat? Okay. Well, before we do that, let me ask this. Maybe all stars act like this. Let's go with crazy ideas. And let's say, let's try another star and see if we end up with that same dip. Okay, maybe it's this star that's acting funny. Okay, so we take a check star, and we treat that check star the same way we've treated our target star. Okay, so here's our target with our nice happy dip. Here's our check star. That's a pretty good line across here. There are a couple of points where it's kind of junky, and we could go in and check those images and see what went wrong. But for the most part, it's this nice straight line. Scale is the same on these, except for I didn't change that one over. But the scale is the same on this, about the same on this as on these. And here's our simulated exoplanet transit. These two match, this one doesn't. This is remaining constant like we expect. All right. So we didn't disprove our theory that time. We don't get to do new science. All right. But like I said, it should repeat. So here's an observation from July 14th, 2008. October 4th, 2008. June 19th, 2009, and August 14th. So we're seeing it's very similar. This one's a little different, but for the most part, we're seeing the same thing over and over again. Now, maybe it's space aliens and somebody's got a little gun that they're pointing at the star. Yes?
How do you distinguish transit dimming from sunspot dimming?
How do we distinguish transit dimming from star spot? It would be a star spot. Star spot dimming is going to be much smaller, much smaller effect than this, except for maybe in very small stars. But also the period is much too short to be a star spot. The star would have to be rotating extremely fast. All right. So, since this has been so much fun, maybe you would like to play the home game. Okay? This is a project that is being developed by Los Cumbres Observatories. It's called Agent Exoplanet. It will allow you to go ahead and perform the photometry on stars. And so we'll have data sets in there for you. And all you have to do is move these little calibrator stars around. Those are our reference stars, as I put it. Sky, target, and you'll be able to make your own light curves out of this. And I probably better not go into that any more than that because we're running out of time. Yes?
I have a question. How many, what's your hit rate? Like, in other words, a lot of stars don't have transiting planets, and you must just take guesses, I guess?
What they do is, actually, I will get into that in one moment.
Oh, right.
Okay. Just after this. So, well, let's assume it is a planet. Then what do we do? Well, with transits, we can accurately determine the period. Okay. Our assumption is that we understand stars and gravity. We know how far the planet is from the star now. We can start talking about how hot it is because we know how hot the star is. We know how far the planet is. We can get a grip on how warm this planet is. Maybe it's warm enough for life. All right? This is a project that is being developed here at the Institute for Astronomy, and Jeff Kuhn is the lead on this. It's the Planets Telescope. I'm not going to go through the acronym, I'm sorry. But this new telescope has been proposed for the summit of Haleakala, and it will use polarized light in order to allow us to look at just the planet. we'll be able to measure the temperature of the planet and then compare that to the orbit and what we predict from the planetary dynamics. We'll also be able to tell what the planet is made of. We'll be able to look at the spectra and look for the thumbprints of the different chemicals that are in that planet. Very nice, very exciting project. And knowing Jeff, he'll let students work on this telescope. That about right? Students are building it. Oh, even better yet. Yeah. So a very exciting thing that's coming up. Here's another thing that's kind of exciting. This is some relatively new science. When I was in school, and I think when all of you guys were in school, we were taught that the solar system formed. There was a cloud. It collapsed, started rotating the same way that as an ice skater pulls in his or her arms, they'll spin faster. Because it's collapsing, it spins faster, forms a disk, and then the planets form in the region of this disk. And here are some observations of that. So these are protoplanetary disks that have actually been taken, and this line through the middle, that's where the protoplanet, where that disk is, where the planets will form.
Were those two different stars?
These were two different stars, correct. I don't remember which stars they were. Google protoplanetary stars, and look at the images. That's what I did. So the star is spinning like this. The planets should be all orbiting in the same way that the same direction that the star is spinning, right? From our models, from this description. But here's some interesting observations. This is fairly new science. Here's a star, and using spectroscopy, you can actually determine the angle of this planet's orbit. And so here's the star spinning like this, spinning this way, and here's the planet looping around like this. Well, that's interesting. And it's not just one case. Here's 6 more. And so apparently a lot of star systems are like this, where they're not like our planetary system, where all the planets orbit around kind of in the same direction that the sun rotates. All of our planets are in a fairly narrow disk, which is one of the reasons I don't think Pluto's a planet. But anyway, okay. Here's another one. Here's 2 of the planets orbiting at big angles relative to each other. Yeah.
Has it been observed a planet and a star orbiting in the opposite direction?
So basically, so the question is, has it been observed where there's a star rotating in one direction and it has a planet orbiting the other direction? I don't know if that has been. It would take quite a lot to do that. Most of these cases are probably collisions. And for this, we might imagine that the angular momentum might have been conserved between these 2 planets. Okay? Yes? How do we know the spin axis of the star? Well, in these cases, right here, it's basically you look at spectral lines, and when the star, when you have a point here, this point is coming towards you. The planet, when it blocks that, will block that blue shifted light. And so by looking at the shape of the spectral line throughout the transit, you can measure the orientation of the transit compared to the rotation of as compared to the rotation of the star. I have not done it. Tim Brown at Las Cumbres has done this, and some other people I know have worked on this. And this will be something that can come out of planets, so we'll be able to do it here. Am I right? This could come out of planets? Sure. But it would be kind of a waste because planets will do a lot more. We had another question over here. Yes.
So these are not part of a galaxy, or are they just randomly?
These are all, okay, all of the targets, all of the exoplanets, planetary systems that we're observing are in our own Milky Way, and in fact, they're in our neighborhood of the Milky Way. The stars become too dim very far beyond that. It's just too difficult to see them. And you need to have an isolated star in order to determine it's an exoplanet. Yeah.
What's the average distance? 100 light years?
The average distance to these exoplanets? I don't know. 100 light years is probably not a bad number. But it's not that there are more planets near us. It's that they're easier to see when they're near us. Okay. Yes.
Are there certain traits of stars that you would study for possibility of exoplanets, or there are some stars that don't give you this spell and more likely don't have exoplanets?
Okay, so the question is, are there certain characteristics of stars that would indicate to us that there are exoplanets before observing the exoplanets? I would say offhand that it might be if they are metal rich, but I don't know. I don't know. I've been doing some other things with the exoplanets. And we have a question online. Wow.
Yes. What is the average size of an exo?
What's the average size of an exo? I would say a typical exoplanet that we know of are these Jupiters. These hot Jupiters are fairly common. But our detection bias, it's easier to detect the hot Jupiters. So for the real distribution, I don't know. Maybe somebody's done some models to explain that, but I don't know. Okay. So, very interesting new science. So, what does it take to find an exoplanet? This goes back to your question. All right? Well, let's talk about a satellite that was put up by the French, COROT. And there are other teams that do this, but the COROT is one satellite. COROT stands for Convection, Rotation, and Planetary Transits. It's also very similar in French. Was put up by CNES in collaboration with the European Space Organization and others. Their real claim to fame is they do very high precision photometry. They measure how bright a spot in the sky is very precisely. They look at a fairly large field of view, 2.7 degrees and by 3.05 degrees. That's bigger than the Pan-STARRS Observatory, if any of you are familiar with Pan-STARRS. I mean, you put up your thumb on the sky, okay, they've got a field of view larger than the width of your thumb. The Falks telescope, by comparison, if you put your little finger up on the sky, about 6 of the images will fit across your little finger. Okay? But their spatial resolution is very poor. Their spatial resolution is 15 arc seconds by 25 arc seconds. So in other words, it's blurred. And let me show you what that means in a moment. And here's a nice image of the satellite. All right, so here's a star field. This is not actually one of the COROT targets, but it's a comparable star field. Okay, their field of view, it looks about like that. That is how big a star would appear to them in their images. And so let me blur this out. That's what they're seeing from that star field. Okay, let me go back here. So you see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, something like 10 stars in that field of view. But now that I've blurred it, you maybe see one, you'd guess 1 or 2 in that field of view. Okay? And this is actually a little misleading because I've had to change the contrast. So they can't see how many stars there are in that area, and if they detect a transit in there, they can't tell which star it is. So they need some people to help by doing ground-based follow-up. So here's our team. Alexis, Regina, Connor. Connor, by the way, is from Maui. Let's give our Maui boy a hand. And Malia. And the Falks Telescope North. Now, the Falks Telescope North, I was checking on the site a little earlier today. Typically, there's a lot of follow-up being done by WISE and CFHT. So WISE is a satellite, not as big as Falks, I don't believe, but CFHT is over 4 meters. So I like to think of this as the little telescope that could, because it's competing with some of these bigger projects. So your task, should you choose to accept it, okay? What we're going to do is we're going to do the photometry on each of these stars. Okay, and like I said, I'll be completely honest, this is actually another field. But these graphs that I'm going to show you are real data of a real target that we were doing confirmation for coral. Okay, so there's the first target. How many of you think that's the exoplanet? Okay. Maybe, yeah. Meh. Well, now, remember, we don't necessarily get the full transit. So this started a little ways, about here's the minimum of the transit. Yeah. This is the kind of thing we're looking for. So, but you'll notice this one doesn't change very much. This one doesn't change very much. This one changes quite a bit. Where? The transit, yeah. Yeah, it started about halfway through the transit. And that was what was predicted. So there you go. There is the confirmation. And these are graphs that were made by that team I just showed you. All right? And also, I was going to do this on the previous slide. The Crow team, they have to keep their data confidential, because if somebody else finds out what their predictions are, they could go out and observe them and scoop them on the discovery and claim them as their own. So they were nice enough to allow me to go into to give me a password to go into their database and get these targets for the students here in Hawaii. And so let's give them a round of applause for, pitching in on education. Isn't that a good team?
Applause coming in from here, too.
All right. All right, so here's what everyone asks. When we start talking about exoplanets, is there life out there? Well, do you believe in flying saucers? Right? Okay. So let's talk about what does it take to support life on a planet. Okay? We believe that life's going to be on planets. What we kind of agree on is water probably needs to be in 3 phases. It needs to be a solid, liquid, and gas. It needs to kind of span those 3 phases. That's the right temperature for a planet. Okay? It's called the triple point of water. And, And so we define that distance from the star as the habitable zone. Okay? For water to form, for water to be ice, it can't be too close. And for water to be a liquid, it can't be too far. It has to be just right. And so they call these planets the Goldilocks planets. Earth is the Goldilocks planet. It's not too far. It's not too close. It's just right. Okay? But here's a question. What about an elliptical orbit? Comes in closer to where it's too hot and then it goes out farther where it's too cold. Would that support life? Yes, could. Those are two good answers. What do you think?
Depends on the reflector.
Extremophiles. Yeah.
I think that here on Earth, they've tested that at really, really cold and really, really hot.
Right. Yeah. So the point that's being made is that there are extremophiles which can survive very hot, the geysers in Yellowstone, for example, just below boiling, and you'll find algae and bacteria in them, and you'll find fish up at the North Pole which have basically antifreeze in their blood. Was that the question? Comment?
Yes, and they also agree with that.
Yeah. All right. Did we have another question or comment from the back? Okay, good. All right. Other thing that, it can't be too big, it can't be too small. Okay? A planet that's too small won't hold an atmosphere, and so you can't have liquid water with no atmosphere. Planet that's too big starts sucking up everything around it when you have a protoplanetary disk, and it becomes more of like a gas giant. Okay? So for an intelligent civilization to develop, we're going to say it needs to be about 0.8 to twice the size of the Earth. These are estimates. We don't know. Okay? How too small is too small to detect? Well, we can just barely detect planets this size. Corot, for example, was designed hoping to find some planets of this size. And I think that I think that the smallest one detected so far is about twice as massive as the Earth. So we're beginning to get to the range where we can detect planets that can support life, where they could develop into civilizations. Okay? But since it's in the habitable zone, since we want our planet to be in the habitable zone, let's imagine observing the Earth as an exoplanet. So we're orbiting some other star, and we're seeing the Earth transit the sun. Well, it will transit once a year, right? And so how many years do we have to observe the Earth before we start saying, yes, it's a planet? It's going to take many years. What? Yeah, okay. All right. But what might be interesting is what about an exomoon? These large Jupiters are easier to detect. If one of them has a moon and it's in the habitable zone, that might be interesting. There actually was a prediction that the first exomoon will be discovered within the next 10 years, and I think that was made a little over 10 years ago, and we still haven't gotten an exomoon to my knowledge. But these can be measured using transit timing techniques. So maybe as we're watching the planet's orbit, it shows up early because its moon has kind of thrown it forward. And then on the next orbit, it shows up late because it's fallen behind and its moon is in front of it. Okay? And that is exactly, you remember Travis, this is what his project was measuring these transit timing variations. All right. So back to life. The Drake equation. This is an equation that was created by Frank Drake in order to predict the number of intelligent civilizations in the Milky Way. And basically what you start to do is you say, well, how many stars are there? N. And it's actually phrased a little differently, but you say, how many stars are there? How many have been stars long enough for a civilization to form? What fraction of them will actually form civilizations? Okay? I'm not going to go through this equation very much because I'm already running over. Well, from the Drake equation, reasonable estimates are 10 or 100. Let's use 100. 100 civilizations in the Milky Way, yes. In the Milky Way. in our galaxy. And for some other reasons I won't go into, we also think that there's a habitable zone in the galaxy. You can't be too close to the center. You can't be too far away. And so we'll just say that these 100 civilizations are on this habitable ring around the Milky Way. On average, they would be about 25,000, the habitable stars would be about 25,000 light years from the galactic center, and our nearest neighbors on average should be about 15,000 light years away. Or sorry, 1,500, 1,500 light years away. Yes?
How far are we from the galactic center?
Somewhere in that range. Does someone, if someone knows a better number, I'll take it.
25,000.
Yeah. That Jeff's nodding. That's about right. Yes.
So from this information, you can safely assume that there's no possible way how that ring would like get to any sort of civilization.
Okay, so let me repeat that, because that's exactly my point. From these numbers, there's no way that we're going to get to reach another intelligent civilization. How about them reaching us? No, probably not, unless they know different laws of physics. It's certainly not going to be like Star Trek, where we get in our spaceship and then 2 days later we go visit another planet with an intelligent civilization. If there are spacefaring alien and intelligent life forms out there, they're probably more like the television show V, where they all got into a big, huge spaceship. They went for a long time. There were generations that passed before any of them saw the next planet. That's what I think that it would be like. All right? So would another society come to Earth? I think there are two reasons they might come here. One, if they knew that we were here, they might come to visit. Okay? This is really a dedicated visit. Okay? Now, the light bulb was invented in 1879. Radio was invented in 1866. These signals travel at the speed of light. Have they had the 1,500 years time to get to that next intelligent civilization? No. It's very unlikely that this neighbor's civilization has detected these signals. Okay? Another reason is maybe they know it's a habitable planet, so they're going to stay here. I would say that they might do that. And so they would come and they would look, and they would send a postcard home. This is what the typical surface of planet Terra looks like. This is our new home. You know, after 1,500 years in a spaceship, minimum, and that's minimum, I'd want to get out for a rest stop. And I don't think you'd get me back in that spaceship. So I think they'd be planning on staying. And let me finish this talk with a discussion from one of my childhood heroes. Richard Feynman was asked about flying saucers. And so let me see. This is a video on YouTube that if you Google Feynman and flying saucers, you should be able to get that. Maybe this is coming from our neighbors, our neighboring exoplanets. Ah, here we go. And I apologize, I forgot to set up speakers in here. Okay, well, I'm losing patience with this. I'll tell you what he said. So you can go home and Google YouTube and Richard Feynman and flying saucers. And what he says is that he had a discussion with Lyman. And Lyman wanted to know what if he believed in flying saucers, and because Feynman's a scientist and he knows all about flying saucers, right? So Feynman looked at him and he said, "No, I don't believe in flying saucers." He He said, well, can you prove it's not, that there aren't flying saucers? And he said, no. It's not about proving and disproving. It's about science is about saying what's likely or unlikely. And he said, well, if you can't prove it, then you're being very unscientific. And he said, no. Think of it this way. I think that the report of flying saucers, the reports we have of flying saucers, I think it's more likely that those are due to the known irrational nature of the human mind rather than the known rational efforts, or rather than the unknown rational efforts of extraterrestrial life forms to reach us. And I think that that's a great way to conclude our discussion on exoplanets. And so, thank you. Do we have some questions? I think we have one from our virtual audience.
What's the most Earth-like discovery today of an exoplanet?
I don't know. Google it. That's literally what I would do. Is I'd just go sit down and Google it.
My hit rate.
Yeah.
The hit rate question.
Hit rate question?
Yeah, you never answered it. I picked up. Like how many hundreds or thousands of stars do you have to investigate before you find the transit?
Yeah, that was my answer to it. So the question is how many stars do we have to investigate in order to find a single transiting exoplanet? A lot. They look at very dense regions with coral. So there's a lot of stars in their field. And they do the photometry on, thousands, if not millions of stars. Okay, and they just sit there and stare at it. What fraction of stars have transiting exoplanets? I don't know. Very low, very small fraction are actually, because they aren't lined up. It's very rare they line up. Yeah, I was working on exoplanets before we started working with Coro. There are other teams that do this. WASP, HAT, Kepler. What are some...
We just asked about Kepler.
Oh, okay.
Why didn't we mention them? So there you go.
Okay, there we go. Yes,
They just kind of hop back.
All right. So yeah, there are a number of other teams, and if I've forgotten somebody, there are a number of teams that have done this and have been very good. And so, yeah.
With both the spectral and transiting, how do you account for multiple planets that might be there, where they might perturb the sun or the star differently, or not perturb its orbit, so it could wobble, or transit several times and that'll totally mess up the Earth?
Right. So your question, if I'm understanding correctly, is let's say we have a star with multiple planets. And since there are multiple planets, it would confuse the signal of transiting or the spectrum. Well, for transiting, it's actually fairly easy. It's very unlikely that they will continue to transit at the same time. And so you'll see two transits. And I think there is a system that does have two transiting exoplanets. It's very rare that both of them line up that precisely. For spectra, when you're using Doppler shift methods, you're dominated by the larger of the two planets, generally. And then once you filter out that signal, you might still see another wobble that's left, and that would be your other planet. It becomes a little difficult, but you can separate them out. You can separate out the signals.
A system that had, 6 or 8 planets, that'd be hard to...
Yeah. Yeah, so if there were 6 or 8 planets around the same star, and they were all these Jupiter-sized things, it would get messy very quickly. It would. Yes.
It makes me think about if you go out to WASP-A and you're standing there and you're looking back at the sun, and we have are we the exoplanets for them? And
Yeah.
you would see all of our planets. How would they know? Because we're in such a small disk, right?
Yeah. So if we were out at some other planet like WASP-A, orbiting another star, and we observed our own planetary system, we've got all of these planets orbiting. But really what we would mostly notice is Jupiter, and then Saturn, Uranus, Neptune. We notice the big guys. Of course, they're very far out. And so this, our solar system, it would be very difficult to detect the planets because they take so long, the large ones take very long time to orbit. Okay? But yeah, it would be a mess. But you can start to see Mercury with its short period versus Pluto or Neptune. Let's say Neptune with a very long period. You can see how you would start to separate those two out because of the difference of the periods. But it would be nearly impossible to detect most of the stars in our system. Let me go back here.
Now, like when you guys are searching for the exoplanets, when you are looking at a certain star,
Mm-hmm.
do you use more than one of the techniques on the star before you move on to the next star, or are there like certain people who just like say like, no, I'm using this technique after a certain one star?
Okay, so when we're looking at for exoplanets in a star field, or a star, typically we start off with a single technique. And then if we see a transit, say Coro's looking at these transiting stars, or transiting planets, if it detects one, then we'll confirm it, and we'll say, okay, this is the star that has the transit, and look at the light ratios, go as far as we can with just the transit. But then we can look at the spectrum and learn a lot more about the system. So we will add on to it by looking at other methods, okay, if they're appropriate. We had a
Couple things. Miller says that Gliese 581 is a confirmed candidate to have life, I guess. One of the answers I was looking for.
Gliese, yeah, Gliese 581 is a planet in the terrestrial, the habitable zone.
And Blue Wall is asking, is there any clues in the shapes of stars to show which ones might be good candidates for study?
Are there any clues in the shapes of stars that might indicate that they're good for study? There are very few stars that we get the shape of the star. Okay, let me go back to this slide. All right. If I can do it. Okay. Remember, there's only those. I could only find 4 stars that we've actually resolved. Most stars are a single point of light. They're not resolved. But there are characteristics about stars that might indicate a higher probability of having planets. Maybe a certain spectral type, metallicity, how much of the star is composed of elements that are not hydrogen and helium. Those characteristics might indicate a higher probability of planets.
Also, just in regard to the plane of the orbits of the planets, does
Mm-hmm.
have any indication? That is in regards to the plane of the orbits of the planets, I think is what he said. Can you say anything just about orbits? Are they all over the place? Are they?
Yeah, so the plane of the orbits, let me show you that slide again. Where did we go? Okay. And for some reason, it's not letting me close this and see if that, there we go. All right. So this seems to be more common than what we find in our solar system, is that these orbits don't form a plane. Okay? we're beginning to believe that it's more common to have more of a halo of planets than a ring of planets like we have. Okay? This is still new, emerging, happening science. And so in 5 years, you might very well be able to come back to me and say, hey, JD, you were wrong. And I'll have to say, okay. Yes?
With all this photometric data, has anybody discovered any features on the surfaces of other stars from this by the shape of the curve?
Okay, so has anyone detected any features on other stars by the shape of the curves?
The photometric curve.
Yeah, the photometric curves. That's actually a project that some boys from Maui were working on. They took that to the Intel International Science Fair this last year, and they had a lot of people say that it was a very good project, and some of the people from the Institute for Astronomy suggested that they publish it. To my knowledge, though, not so much. I mean, there are certainly some features that we can see in the transiting exoplanet. Okay, let me go into, for example, we see this bowl at the bottom. All through this bowl, that planet is blocking part of the star. But because the star is brighter towards the center, if we think of the star as this disk, it's brighter towards the center than the limb, we see it actually get darkest when it's closest to the limb because it's blocking more light. So you can actually think about looking at the limb darkening of stars using exoplanets as occulting disks. You can also find star spots in principle because it would be blocking less light where there was the star when it covered the star spot. In principle, it can be done. I don't know of any features that really have been studied using transiting exoplanets to date. Yeah.
Does the noisy end pieces on the ends of the curve there tell you anything about the solar corona then?
Well, the star's corona. So the noisy things on the end, does that tell us anything about the star's corona? Probably not. This really should be a constant value, something like this. Okay, and that's just noise from the atmosphere is the most likely cause of that.
Are there exoplanets around double stars?
Are there exoplanets around double stars, binary stars?
Binary stars.
Yes. WASP-2b is if I recall correctly, is a binary star. The planet is very close to one of the two stars, and the two stars orbit each other at a very large radius.
They have the same graph then.
Well, this is, yeah. Here it is. This is an example of a binary star. The planet only transits one of the two stars.
I see.
Yeah.
Why, other than the fact that we're here, was there an optimal distance from the center of the galaxy?
Why, other than the fact we're at about this radius, is it that there is an optimal distance from the center of the galaxy, the galactic habitable zone? In too close to the center, stars are packed very closely together. They're all passing by each other. And we think that that would disrupt the planets orbiting the stars. So you have a star, you have a planet orbiting, another star comes very close, it's going to change that planet's orbit very dramatically and make it very hard for a civilization to develop there. Too far from the center of the galaxy, and you don't have processed matter. You only have hydrogen and helium. The carbon in our bodies, the silicon in the sand, the oxygen that we breathe, all of these were processed in stars. All of these elements were created from hydrogen and helium in the center of stars. And then those stars blew up and returned part or all of that material back into the interstellar medium, and then new stars formed with this contamination or this flavoring, this seasoning of oxygen and iron and silicon and carbon, all these other elements that require life. So too far away, the stars aren't close enough together to get that seasoning in there. Does that make sense? Okay. All right.
So we give JD a chance to finish his pizza, and he'll be around. You're not going too quick, so
No, I'll be around.
Questions, get up and stretch your legs. Thanks again.
All right. Thank you.